This is SpaceTime Series 27, Episode 147, for broadcast on the 6th of December 2024. Coming up on SpaceTime, the strange stellar explosion that highlighted the cosmic past, how Jovian moon volcanoes may control Io's insides, and America's next mega rocket goes vertical. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have been given a rare peek into the early history of the universe thanks to a rather unusual supernova event. The stellar explosion involved the core collapse of a bloated ancient red supergiant star on the outskirts of a nearby galaxy. The unusual supernova, called 2023 UFX, represents the most metal-poor stellar explosion ever observed. A report in the Astrophysical Journal indicates the host galaxy also has an extremely low level of metallicity. Now, astronomers refer to all elements other than hydrogen and helium as metals. The study's lead author, Michael Tucker from Ohio State University, says that since the metals produced within supernovae inform their properties, including how stars evolve and die, learning more about their formation can tell astronomers much about the state of the universe when it began, especially since essentially there were no metals around during the time of its birth. Tucker says if you want to predict how, say, the Milky Way came to be, you need to have a good idea first of how the first exploding stars seeded the next generation. He says understanding that gives astronomers a great example of how those first objects affected their surroundings. And this is where dwarf galaxies come in. They're especially useful as local analogues, showing the conditions scientists might expect to see in the early universe. Because of them, astronomers know that while the first galaxies were metal-poor, all the big, bright galaxies near the Milky Way had plenty of time for stars to explode and therefore increase the amount of metal content. The amount of metals a supernova has also influences aspects of the number of nuclear reactions it may have, or how long its explosion remains bright. It's also one of the reasons that many low-mass stars also occasionally run the risk of collapsing into black holes. Typically, any metal-poor supernova that astronomers would expect to find would likely be too faint to be seen from our galaxy because of how far away they are. Now, thanks to instruments like NASA's Webb Space Telescope, detecting distant metal-poor galaxies is much easier. The observations of 2023 UFX revealed that many of its properties and behaviours are distinctly different from supernovae in nearby galaxies. For example, it had a period of brightness that stayed steady for about 20 days before declining. On the other hand, the brightness of its metal-rich counterparts usually lasts about 100 days. The study also showed that a large amount of fast-moving material was ejected during the explosion, and that suggests it must have been spinning very quickly when it exploded. This result implies that rapidly spinning metal-poor stars must have been relatively common during the early days of the universe. Tucker and colleagues think the supernova likely had weak stellar winds, streams of charged particles emanating from the star's atmosphere, and that led it to cultivate and release so much energy. Overall, their observations are providing the groundwork for other astronomers to better investigate how metal-poor stars survive in different cosmic environments, and may even help some theorists more accurately model how supernova behaved in the early universe. This is SpaceTime. Still to come, how Jovian moon volcanoes may help control Io's insides, and America's next new mega rocket goes vertical. All that and more still to come on SpaceTime. A new study has found that the Jovian moon Io has active volcanoes at its poles which may help regulate internal tidal heating. Io is the most volcanically active world in the solar system. It's a place where instead of weather reports, you'd have volcanology reports, with say lava fountains to the north or magma lakes forming in the east. By staring into the hellish landscape of Io, astronomers have been able to study a fundamental process in planetary formation and evolution, namely that of tidal heating. Tidal heating is caused as a body, like say Io for example, is constantly being crushed and stretched as it orbits through the massive gravitational field of its host planet Jupiter and other nearby moons. all this pushing and pulling causes lots of internal friction, and that causes heating. Tidal heating plays an important role in heating and orbital evolution of celestial bodies. It provides the warmth necessary to form and sustain subsurface liquid water oceans in the moons around some of the gas giants, like Jupiter's Europa and Saturn's Enceladus. The study's lead author, Madeleine Pétain from Cornell University, says that studying the inhospitable landscape of Io's volcanoes even inspires science to look for life. By examining flyby data from NASA's Juno spacecraft, Pétain and colleagues discovered Io's active polar volcanoes may be helping to regulate tidal heating, and it's that heating which causes friction in the moon's magma interior. The observations, reported in the journal Geophysical Research Letters, shows that Io has a surprising number of active volcanoes at its poles, as opposed to those in the more common equatorial regions. In the north, a cluster of 4 volcanoes, Acis, Zal, Tonatiuh, and one unnamed volcano, and an independent one named Loki, were all highly active and persistent, with a long history of both space-based and ground-based observations. A southern group of volcanoes, Khanheliki, Utar, and Lakioi, also demonstrated strong activity. The long-lived quartet of northern volcanoes was seen to concurrently become bright and seem to respond to one another. Pétain says they all got bright and then dimmed again at a comparable pace. She says it was fascinating to see these volcanoes acting in unison and seeing how they respond to each other. This is SpaceTime. Still to come, America's next mega rocket goes vertical, and the December solstice, the ticking time bomb of Eta Carina, and the rock comet Phaeton are among the many highlights of the December night skies on Skywatch. America's latest mega rocket, Blue Origin's New Glenn, has been hoisted into its vertical position on its launch pad in preparation for its hot fire test in the lead-up to its maiden flight later this year. The 98-metre-tall launch vehicle is the latest in a series of massive heavy-lift rockets being developed in the United States to carry huge payloads into orbit and beyond. It'll eventually join NASA's SLS Orion moon rocket and SpaceX's Starship Super Heavy in setting new standards for launch capabilities. The upcoming hot fire test will allow mission managers to test both the rocket itself and the launch pad ground systems at the newly built Space Launch Complex 36 at the Cape Canaveral Space Force Base in Florida. New Glenn, which is named after John Glenn, the first American to achieve orbital spaceflight, was carried horizontally from its vehicle assembly building to the launch pad by a new specially built 91-metre-long, 1,814-tonne transporter erector vehicle. The maiden flight had originally been targeted for last month, but it was bumped back to this month because of ongoing technical issues. The launch is the first of 2 tests needed to get certification by the United States Space Force to fly national security missions. New Glenn is designed to lift payloads of 45 tonnes into low Earth orbit, 13.6 tonnes into geostationary transfer orbit, and 7 tonnes into translunar orbits. Blue Origin plans to land the first stage of New Glenn on a floating barge after launch for eventual refurbishment and reuse. That's similar to how SpaceX lands the first stage of its Falcon 9 rockets. Blue Origin have been perfecting the manoeuvre on their smaller New Shepard rockets, which are used for space tourism flights out of Texas. New Glenn's first stage booster will be powered by 7 B-4 engines, producing up to 3.9 million pounds of thrust. Now, this same engine's also being used on the United Launch Alliance's new Vulcan Centaur rocket. The booster is designed for reuse up to at least 25 times. The second stage, which is non-reusable, will be powered by 2 BE-3 engines. They're based on the same engine used aboard New Shepard. And a third stage, using a single BE-3 engine, is now also in development for eventual use on the new rocket. This is SpaceTime. Time now to turn our eyes to the skies with December Skywatch. December is the 12th and final month of the year in both the Julian and Gregorian calendars. December got its name from the Latin word decim, meaning 10, because it was originally the 10th month of the year in the old Roman calendar, which began in March. The astronomical highlight of the month is the December solstice, which this year occurs at 20:20 Australian Eastern Daylight Time on the evening of Saturday, December the 21st. That's 4:20 on Saturday morning US Eastern Standard Time and 9:20 in the morning Greenwich Mean Time. This is when the Sun appears to reach zenith directly over the Tropic of Capricorn. In the United States, in the Northern Hemisphere, it marks the winter solstice, signifying the first day of winter. But the good news is that from now on, the days start to get longer again. On the other hand, south of the equator, summer has well and truly arrived, and the days are usually at their warmest. Earth's seasons occur because of the tilt of the planet's spin axis, which is inclined at 23.4 degrees in relation to the Sun. Now, generally speaking, Earth's axis always points to the same position in space, regardless of the position of the Earth as it orbits around the Sun. So on the day of the December solstice, the Earth's south pole is tilted towards the Sun, so its southern hemisphere gets more daylight and more direct sunlight, so it's hotter and its southern hemisphere is in summer. 6 months later, during the June solstice, the north pole is tilted towards the Sun, and so it's the northern hemisphere which experiences summer, while the southern hemisphere gets less daylight, longer nights, and the sunlight strikes the surface of the planet at a shallower angle, meaning less heat, and so the southern hemisphere is in winter. In between these two, we have the March and September equinox. That's when the northern and southern hemispheres get roughly equal amounts of daylight and heat, giving us the seasons of spring and autumn. Now earlier we said that generally speaking, Earth's axis always points to the same position in space, regardless of Earth's orbital position around the Sun. And while that's true in our day-to-day lives, over geologic time, approximately 25,772 years, a gravity-induced effect known as axial precession causes a slow and continuous change in the orientation of Earth's rotational axis. You can see the same effect in the precession of a spinning top as its axis traces out a pair of cones joined by their aspices. Earth's precession was historically called the precession of the equinoxes because the equinoxes moved westwards along the ecliptic relative to the fixed background stars. This slow precession of the Earth's axis means that over 25,772 years, the positions of the south and north celestial poles appears to move in circles against the space-fixed background stars. So, while today the star Polaris lies approximately at the north celestial pole, this will change over time, and Gamma Cephei will ultimately become the North Star in about 3,200 years from now. It also means the seasons would slowly move through different calendar months, but we make adjustments to the calendar to compensate for that. In most parts of the world, the seasons begin on the day of the solstice or equinox. However, Australia's a bit different. We're a bit strange. Instead, here, seasons start on the first day of a particular calendar month. That means the 1st of March for autumn, 1st of June for winter, the 1st of September for spring, and December the 1st for summer. Because of the relatively small amount of elongation in Earth's orbit around the Sun, Earth's seasons are determined by its axial tilt rather than orbital distance. Currently, Earth's closest orbital position to the Sun, known as perihelion, occurs about 2 weeks after the December solstice, and its furthest from the Sun, known as aphelion, about 2 weeks after the June solstice. Now that means the next perihelion will occur at 12:28 a.m. on the morning of Sunday, January the 5th, 2025, Australian Eastern Daylight Time, when planet Earth will be 147,103,686 kilometres from the Sun. That's at 8:28 a.m. on the morning of Saturday, January the 4th, US Eastern Standard Time, and 1:28 in the afternoon, Greenwich Mean Time. Like axial precession, Earth's orbit also changes gradually over geologic time, getting more or less elongated and changing perihelion and aphelion. Even the degree of the tilt of Earth's axis changes over thousands of years. Now, collectively, all these changes are known as Milankovitch cycles, after the Serbian geophysicist and astronomer Milutin Milankovic, who in the 1920s hypothesized that variations in eccentricity, axial tilt and precession resulted in cyclic variations in solar radiation reaching the Earth, and that this orbital forcing strongly influenced Earth's climatic patterns. Okay, let's start our tour of the December night skies in the west, where midway up from the horizon is Fomalhaut, the brightest star in the constellation Pisces Austrinus, the southern fish. Fomalhaut is a very young white spectral type A main sequence star, about 1.8 times the diameter of the Sun, and located reasonably nearby, just 25 light-years away. Now, main sequence stars are those undergoing hydrogen fusion into helium in their cores. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our sun fits in by the way. Then comes spectral type K orange stars, and the coolest and least massive known stars are spectral type M red stars. Now each spectral classification can also be subdivided using a numeric digit which represents temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. So our Sun is a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red dwarf stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or roughly 0.08 solar masses. In 2008, astronomers detected planets orbiting around Fomalhaut. At this stage, it's not known if anyone was looking back. 5,000 years ago, the ancient Mesopotamians used Fomalhaut to mark the northern hemisphere's winter solstice. Now turning to the left of Fomalhaut is Akin or Alpha Eridani, the brightest star in the constellation Eridanus, the river. Located 139 light-years away, Akin has 7 times the diameter of the Sun and rotates some 15 times faster, giving it a very obvious oblate shape. The effect of this rapid rotation is that the star flattens at its poles but bulges in the middle. In fact, its equatorial diameter is about 50% greater than its polar diameter. It turns out Akin is actually part of a multiple star system, Alpha Eridani A and Alpha Eridani B. The primary star, Alpha Eridani A, is a hot blue spectral type B main sequence star. Its smaller companion, Alpha Eridani B, is a spectral type A white star. Their pair orbit each other around a common centre of gravity at a distance of about 12 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. Moving further left from Akin and just above the horizon is Canopus, the brightest star in the southern constellation of Carina the Keel, and it's also the second brightest star in the night sky after Sirius. Canopus is a white giant star nearing the end of its life. It's located about 310 light-years away. It has about 8.5 times the mass of the Sun, but it's expanded out to about 71 times the Sun's diameter. Canopus has some 1,300 times the brightness of the Sun, and in fact, it's the brightest star within 700 light-years of Earth. Its name originates in mythology from the time of the Trojan Wars and the navigator for Menelaus, the king of Sparta. Located between Canopus and the Southern Cross in Carina in the Trumpler 16 open star cluster is the ticking time bomb that is Eta Carina, a pair of huge blue stars undergoing the final violent phase of their existence for exploding as massive core collapse supernovae. The binary system is located some 7,500 light-years away, buried deep within the great nebula of Carina, a massive cloud of gas and dust stretching some 6.5 to 10,000 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in an Earth year at 300,000 kilometres per second, the speed of light in a vacuum and the ultimate speed limit of the universe. The stars in Eta Carina are classified as highly luminous spectral type O blue hypergiants. The primary star is estimated to be around 150 to 200 times the mass of our Sun, with some 5 million times the Sun's luminosity, 800 times its radius, and a surface temperature of up to 32,500 Kelvin. The primary star in this binary pair is also the only known star to produce ultraviolet laser emissions. The companion star, although smaller than the primary at just 80 solar masses and 20 times the Sun's radius, is even hotter, with surface temperatures of around 37,200 Kelvin. The two stars orbit each other every 5.54 Earth years, cocooned in a gigantic twin-lobed cloud of gas and dust known as the Homunculus Nebula, a bipolar emission and reflection nebula. The primary star in this binary pair has lost about 30 solar masses in recent times. Both Eta Carina and its surrounding shroud of dust generate huge amounts of infrared radiation, making it the brightest infrared source in the sky. Eta Carinae experiences tremendous outbursts. During one event, it became almost as bright as the star Sirius. Known as the Great Eruption, it began in 1837 and reached its peak in 1843, when it was one of the brightest objects in the night sky, before gradually fading away again by 1856. Eta Carinae underwent another slightly smaller eruption in 1892, and has again been steadily brightening since about 1940. Both these stars are now nearing the end of their lives on the main sequence, and they're expected to go supernova in an astronomically short space of time. When they do go supernova, Eta Carinae will be visible in the daylight skies even here on Earth. In fact, they could become brighter than the full moon for months on end. No one knows exactly when Eta Carinae will go supernova. A single star, a star originally around 150 times as massive as the Sun, would typically reach core collapse as a Wolf-Rayet within about 3 million years. At low metallicity, many massive stars will collapse directly to form stellar mass black holes with no visible explosion, or possibly a subluminous supernova, and a small fraction will produce a pair instability supernova. But at solar metallicity and above, there's expected to be sufficient mass loss before collapse to allow a visible supernova to appear. Now, if there's still a large amount of expelled material close to the star, the shock wave formed by the supernova explosion impacting on the circumstellar material could effectively convert the kinetic energy into radiation, resulting in a superluminous supernova or hypernova, several times more luminous than a typical core collapse supernova and much longer lasting. Highly massive progenitors may also eject sufficient nickel to cause a superluminous supernova simply from the radioactive decay. Now, the resulting remnant would then form a black hole, since it's highly unlikely that such a massive star could ever lose enough mass from its core not to exceed the limit for a neutron star, about 2.3 or 2.4 solar masses. But the existence of a massive companion star brings many other possibilities into play. If Eta Carinae A was rapidly stripped of its outer layers, it might become a less massive WC or WO type star when core collapse is finally reached. This would result in a Type 1b or Type 1c supernova due to the lack of hydrogen and possibly helium. And these supernovae are thought to be possible progenitors for some types of gamma-ray bursts. Now, a typical core collapse supernova at the distance of Eta Carinae would look as bright as the planet Venus, the third brightest object in the sky after the Sun and Moon. On the other hand, a superluminous supernova could be 5 magnitudes brighter, possibly the brightest supernova in recorded history. But I'm pleased to say that, based on our current data, Eta Carinae is not expected to produce a gamma-ray burst, and its axis isn't currently aimed anywhere near the Earth. And at 7,500 light-years away, the star is unlikely to directly affect terrestrial life forms on Earth thanks to our planet's atmosphere and magnetosphere. But the ozone layer of the planet could be damaged, as would orbiting spacecraft and any astronauts in space at the time. At least one paper has projected that a complete loss of the Earth's ozone layer is a plausible consequence, and that would result in a significant increase in ultraviolet radiation reaching the planet's surface from the Sun. But that would require a typical supernova to be closer than 50 light-years from Earth, and even a potential hypernova would still need to be closer than where Eta Carinae is now. Another analysis of the possible impact of a supernova in Eta Carinae discusses more subtle effects from the unusual illumination, such as possible melatonin suppression, resulting in insomnia and an increased risk of cancer and depression. Okay, on that note, let's turn to the east, and looking just above the horizon is the star that outshines Canopus to take the title of the brightest star in the night sky, namely Sirius the Dog Star. And next to it, in the east-northeastern skies just above the horizon, is the constellation of Orion the Hunter. There you'll see a very bright red star. It's a red supergiant called Betelgeuse, better known to most people these days as Betelgeuse. Don't say it 3 times. In ancient times, before centuries of mispronunciation, its name actually started out as Ibdal-Yauza. Betelgeuse is one of the largest and most luminous stars visible with the unaided eye. Located some 430 light-years away, this bloated old red giant is reaching the end of its life. It's truly massive, some 1,100 times the diameter and 100,000 times the brightness of our Sun. Like Eta Carinae, Betelgeuse is destined to explode as a core collapse supernova sometime in the near future. Betelgeuse marks the right shoulder of Orion the Hunter, although it's all upside down from our perspective here in the southern hemisphere. That's because Orion was a hunter in Greek mythology, so the constellation was viewed from the northern hemisphere. The earliest known depiction of the Orion constellation was on a prehistoric mammoth ivory carving found in a cave in the Arch Valley in West Germany. That was in 1979. Archaeologists estimate that it had been fashioned between 32,000 and 38,000 years ago. The distinctive pattern of Orion has been recognized in numerous cultures around the world, including the ancient Babylonian star catalogues dating back to the Late Bronze Age. In Greek mythology, Orion was a gigantic, supernaturally strong hunter of ancient times. He was the son of a Gorgon and Poseidon, also known as Neptune, the god of the sea in the Greco-Roman tradition. But the goddess Gaia became angry at Orion after he boasted that he would kill every animal on Earth. So she sent a scorpion to sting Orion to death. However, Ophiuchus the serpent-bearer revived Orion with an antidote. And this is given to be the reason why the constellation Scorpius chases Orion across the sky, with the constellation Ophiuchus standing midway between them. The other major stars in Orion include Rigel, Orion's left foot, a blue supergiant. Having exhausted its core hydrogen, Rigel has swollen out to between 79 and 115 times the Sun's radius. It's currently fusing heavier and heavier elements at its core, meaning it too will soon likely go supernova and collapse to form a neutron star. Rigel's estimated to be somewhere between 120,000 and 279,000 times the luminosity of the Sun. It's a binary system, located 860 light-years away. And it has a companion star, Rigel B, some 500 times fainter than the supergiant Rigel A and visible only through a telescope. Rigel B itself is a spectroscopic binary system comprising two main-sequence blue-white stars. Spectroscopic binaries are double star systems orbiting each other in such a way they can only be visually separated from our vantage point here on Earth by their different spectroscopic signatures. The two stars making up Rigel B are estimated to have 3.9 and 2.9 times the mass of the Sun respectively. And one of these stars, Rigel BB, may itself also be a binary system. Rigel B also appears to have a very close visual companion, Rigel C, almost identical in appearance. The third brightest star in Orion is Bellatrix, Orion's left shoulder. It's a spectral type B main sequence blue star with about 8.6 times the mass and 6 times the radius of the Sun. Bellatrix is about 250 light-years away. It has an estimated age of about 25 million years. That's old enough for a star of this mass to start consuming hydrogen in its core and begin to evolve away from the main sequence and turn into a blue giant. Now, if you look at the 3 stars which make up Orion's belt, you'll see another 3 stars which make up Orion's sword hanging from the belt, and again, that's hanging upwards for those of the southern hemisphere. And if you look carefully at the middle star, you'll notice it's a bit fuzzy looking. That's because it's not a star, but the Great Nebula of Orion, Messier 42. Located just 1,344 light-years away, Messier 42 is the nearest massive star-forming region to Earth. Its nebula is estimated to be some 24 light-years across, and it has the mass of more than 2,000 suns. The Orion Nebula is one of the most scrutinized and photographed objects in the night sky, and it's among the most intensely studied celestial features. The nebula has revealed much about the process of how stars and planetary systems are formed from collapsing molecular gas and dust clouds. By studying M42, astronomers have directly observed protoplanetary disks, brown dwarfs, intense and turbulent motions of gas, and the photoionizing effects of massive nearby stars in the nebula. The Orion Nebula contains a very young open cluster known as the trapezium due to the asterism of its 4 primary stars. Now, the trapezium itself is a component of the much larger Orion Nebula cluster, an association of about 2,800 stars, all within a diameter of just 20 light-years. One of the most stunning nebula in the constellation Orion is the spectacular Horsehead Nebula, Barnard 33. The Horsehead is a dark nebula located just to the south of the star Alnitak, which is the furthest east on Orion's belt, and is part of the much larger Orion Molecular Cloud Complex. Located around 1,500 light-years away, the Horsehead Nebula was first recorded in 1888. It's one of the most identifiable nebulas in astronomy. That's because of the shape of its swirling clouds of dark dust and gases, which bear an amazing resemblance to a horse's head when viewed from Earth. One of the astronomical highlights of the December night skies is the annual Geminids meteor shower, which usually peaks around December the 13th and 14th. Radiating out from the direction of the constellation Gemini, the Geminids are unusual in that they're not generated by a comet as most other meteor showers are, but are produced by the debris trail left behind by the asteroid 3200 Phaeton. That makes the Geminids, together with the Quadrantids, the only major meteor showers not originating from a comet. 3200 Phaeton is highly unusual. Its high orbital eccentricity more closely resembles that of a comet than an asteroid. And in fact it's speculated that it may be an asteroid that's simply run out of all the volatile gases that normally characterize a comet. Phaeton's orbit crosses all the inner terrestrial planets, Mercury, Venus, Earth and Mars. And because it does come relatively close to the Earth, this 5-kilometre wide space rock is classified as potentially hazardous. Phaeton will make its closest approach to Earth on December the 14th, 2093. But at that time it will still pass a relatively comfortable 2,960,000 kilometres away from our planet. Interestingly, Phaeton's named after the son of the Greek sun god Helios. Legend has it that Phaeton almost destroyed the Earth by stealing Helios' chariot and scorching the Earth with the sun, almost causing the apocalypse. Phaeton approaches the Sun closer than any other named asteroid, with a perihelion of less than 21 million kilometres. That's less than half of Mercury's perihelion distance. Coming so close to the Sun causes the asteroid's surface to reach over 750 degrees Celsius. Observations by NASA's Stereo spacecraft saw dust trails radiating off its surface. And in 2010, Phaeton was detected actually ejecting dust into space. Astronomers think the intense heat generated by its close approaches to the Sun causes fractures in the gravel and rocks on the asteroid's surface, similar to mud cracks in a dry lake bed. And Phaeton's composition also fits the notion of a cometary origin. It's classified as a Type B asteroid because it's composed of primarily dark material. Type B asteroids are thought to be primitive, volatile-rich elements of the early solar system. Its composition, orbit and dust trail have led astronomers to refer to Phaeton as a rock comet. The Geminids' meteors have a yellowish hue, and they tend to be a bit larger and more solid than typical meteors from comets. Think of grains and rocks rather than dust particles. They also move more slowly, travelling at about 35 kilometres per second compared to some cometary meteor showers which travel at speeds of up to 72 kilometres a second. Interestingly, the Geminids are also thought to be intensifying every year, with recent showers seeing up to 160 meteors per hour under optimal conditions. In the Northern Hemisphere, expect to see up to 120 meteors per hour between midnight and 4 a.m, but only from a dark sky. Well north of the equator, the radiant rises about sunset, reaching a usable elevation from local evening hours onwards. In the Southern Hemisphere, the Geminids aren't nearly as spectacular. You won't see as many, perhaps just 10 to 20 an hour. That's because the radiant doesn't rise above the horizon at all. Now, for listeners in the Northern Hemisphere, there's a second meteor shower in December, the Ursiids, which radiate out from the direction of Ursa Minor, the Little Dipper. The Ursiids are generated by debris left behind by the comet 8P Tuttle. They're a compact stream, peaking during the night of December the 22nd and the early morning hours of December the 23rd. If you look towards the bowl of the Little Dipper, you might see about 10 meteors an hour. And now, with the rest of the December night skies, we're joined by Jonathan Nally from Sky and Telescope magazine.
G'day, Stuart. Yeah, well, it is December, which means it's summertime where I live. If you're north of the equator, you're entering winter instead, of course. But where I am down here, it's very hot at the moment. It's going to get even hotter. The thing is, with summertime viewing, is you get fewer hours of nighttime, of course, because the daylight's longer, so night hours are shorter. But at least the weather's good. You don't have to go out in freezing cold temperatures. Look, we normally start our sky tour in the south, but this time we'll start with the sky to the east for this time of the year. So once the sun has gone down and the sky is dark, you look to the east and you will see the mighty constellation Orion the Hunter sitting above the eastern horizon. It's pretty easy to make out because there's a little trio of stars in a row. There's a little straight line of these three stars quite close together. That's known as the Hunter's Belt, Orion the Hunter's Belt. And it's quite easy to see, as are two of Orion's brighter stars. You've got bluish Rigel, which is above the belt as you look at it in the eastern sky, and you've got reddish Betelgeuse, which is down below the belt and sort of down quite low towards the horizon about, 9 o'clock, 9:30 or so, but it rises higher as the night goes on, so you won't have any trouble finding it. These two stars, Rigel and Betelgeuse, so Rigel is the seventh brightest star in the night sky, and Betelgeuse is the 10th, so they are pretty bright. Rigel is big and bright, literally. It's more than 70 times wider than our sun, and it's 120,000 times as bright. But thankfully, it's more than 850 light years from us. Otherwise, you'd be in real trouble. Some of these stars out there, they're just enormous and they're very intrinsically bright, but they're so far away that they just look like stars. You know, if they were closer in, we'd have sort of permanent daylight. We'd have our star giving us daylight during the day, and nighttime. If some of these bright stars are much closer, then you'd be able to read by them. There'd be so much light. Betelgeuse, the other star, it's even bigger. It's around 700 times wider than our sun, and it's more than 70,000 times as bright. So a couple of really giant stars you've got there. Incidentally, I mentioned the sun there in daylight. You do know, don't you, Stuart, that it has been scientifically proven that the moon is better than the sun. Have you heard this?
Okay, why is the moon better than the sun?
Well, see, the moon shines at night when everything's dark, and it gives us light by which to see things, so we can get around at night time. But the sun, well, it only shines during the daytime, and it's light anyway.
What about a new moon?
Now you complicate
You wish I hadn't asked you that.
That was George Gamow. It was a George Gamow joke. That was his name, George Gamow, the famous astronomer Gamow.
He was the one who said if we ever go to the sun, we should only go at night time when it's cooler.
That's right. Now, listen, talking about those stars in Orion, if you start at Orion and you go to the left as you're looking at it in the night sky, which actually means you're going northward, you're looking further to the north, you should see a reddish star that makes up one corner of a triangle or a wedge of stars pointing up from the horizon. Now, that star is called Aldebaran, and the triangle is a star cluster called the Hyades, and they're both part of the constellation of Taurus. Now, if you can get a pair of binoculars, just binoculars, you don't need a telescope, just get a pair of binoculars onto that wedge-shaped cluster of stars, please do so because it's really, really pretty. Binoculars give you just a little bit of extra light-gathering power to see fainter things, as do telescopes, of course, but it's just binoculars on their own. You'll see more and more stars than just the little wedge shape that you can see of probably about half a dozen, 7 or 8 stars or so in the Hyades. Get some binoculars onto it and you'll see a few dozen. And a bit further to the left of the Hyades is another star cluster that we've spoken before about on the program, and it's even prettier, and this is the Pleiades, which is also known as the Seven Sisters, because it's long been said that most people can see 7 stars out of the 1,000 or so that are in this cluster, but all those other ones are far too faint for the unaided eye. You need a telescope to start bringing those out. And it's interesting because it's been given that name, Seven Sisters or something similar, in many different cultures scattered all across the globe and dating from a long, long time ago. And it's been suggested actually that the idea of these little bit of stars being 7 sisters, or some sort of mythology associated with 7 sisters in the sky, that idea originated tens of thousands of years ago and spread around the world as early humans made their way across the planet. And if this is correct, it's probably the oldest mythology for our entire species that has survived to the present day. We're talking, tens of thousands of years, a long, long time back. Because the other interesting thing about this is that even though this group of stars is called the Seven Sisters, most people with average eyesight and dark skies can only see 6. And it's been that way for a long, long time. And it's been suggested that maybe there was a 7th star that used to be brighter a long time ago and has now faded away. The star will still be there, but stars do change in their brightness, so maybe there was a 7th one that was brighter a long time ago. Or maybe there were 2 stars that are now close together, so further apart in the distant past, and so you could see them separately as 2 stars, so you made up a total of 7, whereas now, we only see 6. So it's a bit of a mystery still, that one, but it really is interesting how different cultures around, not all cultures, some cultures have other ideas, other mythologies associated with this little group of stars, but so many of them do associate them with a group of sisters.
7 sisters or 7 women. It always seems to be like that. And in some of these cultures, they're also being chased by Orion the Hunter.
That's right.
He's chasing them. This includes Aboriginal cultures in Australia. It's amazing.
Very, very common story. So it's not impossible that there was a common origin going back tens of thousands of years from somewhere, and that story just travelled, because back in those days, before writing and everything was verbal and mythologies were passed along. So it's interesting. That could be the oldest surviving mythology. Now, turning to the south, we haven't mentioned the south yet. If you look down to the south, we'll see that the Southern Cross, well, you might see the Southern Cross upside down, but for many people, it's below the horizon, sort of mid-evening this time of the year. Certainly for the people in the northern hemisphere, but even people in the southern hemisphere. I mean, I can't see it about 9 o'clock at night where I live. Those at latitudes of around 40 degrees south or further will see the cross just above the southern horizon. But as the Earth turns, the cross will sort of rise in the southeast. So if you give it a few hours, get to midnight or past midnight or so, particularly after midnight this time of year, you will see the Southern Cross starting to come up again in the southeast. It'll be lying on its left-hand side, but the Earth has turned a bit more on its axis. Also in the south, but only if you have dark skies, the two things you really shouldn't miss, and that's the two nearest sizable galaxies to our own. These are known as the Large and Small Magellanic Cloud. You'll find them about halfway up from the southern horizon, and they do just look like faint fuzzy clouds, but they are in fact galaxies full of millions of stars. To the naked eye, you're not going to see any of those individual stars. It just looks like a milky patch. But if you have a telescope, or know someone who's got a telescope, then get a telescope onto them, and you will start to see more detail there, including some fantastic nebulae and star clusters and things. There's quite a lot. These two galaxies, astronomers are very fond of them because it gives us an opportunity to study things in other galaxies, but most galaxies are very far away. These two are close, so it gives us a bit more of a close-up view of how things are in other galaxies. Now, let's have a look at which planets we can see in the evening. There's 3 of them. Venus is the obvious one. It's shining big and bright above the western horizon after sunset. You really can't miss it. It's really big and bright. On the opposite side of the sky, just above the western horizon and near that Pleiades star cluster I mentioned earlier, is Jupiter. It's not quite as bright as Venus, but it's still prominent, very prominent. It has a slightly sort of off-white tinge to it. Probably say you wouldn't call it red or yellow.
Beige sort of.
Yeah, beigey sort of, or maybe even a slight pinkish tinge, but only the tiniest amount. When it's down low on the horizon, you get the murk of our atmosphere changes the colours of things. So wait until Jupiter is risen up higher above the horizon. It's out of the murk of the pollution and dust and everything down in the lower part of the atmosphere, and then you'll see that it looks just slightly off-white. And very high in the northwest in the evening at the moment is Saturn. It's dimmer than Venus and Jupiter. It's not quite as bright. In fact, it's nowhere near as bright. But it does have a telltale yellowish colour. You really can't miss it. And if you do have access to a small telescope, even if it's a tiny one, even a small telescope, take a look, because you should be able to see the planet's rings. And Saturn and its rings always look great through a telescope. And Stuart, that's the sky for December.
That's Jonathan Nally from Sky and Telescope magazine. And this is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.